Hi there. Welcome to Lecture 7 of Machine Learning from Data, Approximation versus Generalization. Now just to recap, the last few lectures have been a tour de force of math and theory to establish that, even for infinite hypothesis sets, we can get this link from E in to E out. Now how did we accomplish that? We introduced this effective number of hypotheses, the growth function, which is polynomially bounded for good hypothesis sets. And that gives us this link from E in to E out. For bad hypothesis sets, you're out of luck. There's a lot of theory out there. And we chose this particular blend of theory. Why? Well, first, it has withstood the test of time. Second, it establishes this fundamental link from E into E out, and we only care about E out. And third, this theory has relevance to practice. If you violate the assumptions of this theory, you will feel it in practice. So it is relevant theory. It's not just space-filling abstract theory. Okay. And, embedded in this theory, well, first of all, is the concept of a good and a bad hypothesis set. Second of all is this concept of approximation versus generalization, the tug of war between E in and E out. You want a large hypothesis set to get E in small, you want a small hypothesis set to get E in close to E out, and you need to balance this tug of war. Okay. So you need to choose, there are choices to be made, and this gives us a theory, a principled way to make those choices. So we'll dig a little bit deeper in this theory, we'll introduce you to the concept of a VC dimension, then we'll study approximation versus generalization, and another way to view that whole concept, which is the bias-variance analysis. So I worked hard, I did some hardcore theory, derived a nice technical result for you, so I feel I've earned the right to preach. So let me preach a little. Okay? And in my preaching, I'm going to remind you of this ancient, Persian saying, okay, which goes as follows. He who knows and knows it is wise, follow him. He who knows and knows it not is asleep, wake him. Okay? He who knows not and knows it is a student, teach him. He who knows not and knows it not is a fool, avoid him. Okay. So now I want to just, I wrote in red the guy who knows nothing, but thinks, they know everything, so knows not that they know nothing. That's the dangerous guy. Okay. On the other hand, what we would like to interact with, are people who know, and they know they know. Okay. It's very dangerous to come upon this red guy. Okay. And a similar situation occurs in machine learning. Okay. And that's sort of what the theory established. Now, we did all this theory, and in practice, there's a tendency for theory to go by the wayside. People, we tend to have the sort of impression, theory, all this math, is it worth anything? Does it have any relevance to practice? Okay. Or is it just a paralysis by analysis kind of situation? Okay. And so, I want to sort of emphasize that when it comes to learning, that's a mistake to throw the theory by the wayside. Now, it may be that, when you're practicing, someone else has done the theory for you and selected a good hypothesis set with this and that property. Essentially what they're doing is they're establishing this link between E in and E out. Okay. And, it's very important, I cannot emphasize more that, there's the side of the world that we can see, so in sample, and there's the side of the world that we cannot see, so out of sample. And on this side lives E in, and on this side lives E out. Okay, and you will never know E out. So this is a black, thick, impenetrable curtain. You will never know E out. Okay. And that's why it's very tempting, it's very easy, it's very concrete to just go and take E in and minimize it, send it to zero. And anyone can do that. You might need to skillfully manipulate your way through a hypothesis set or something like that. But, at least in feasible, it's a concrete task and we can accomplish it. Okay. But when it comes to learning, it accomplishes nothing. Okay. It's just memorizing the data. Okay. What we really care about is this thing that we cannot see. Okay. And so the theory builds this link. Okay. And that link is very important because now if we have this link, we can go ahead and minimize the concrete thing. So when you approach a machine learning problem, one of two things will happen. Okay. And this is what we discussed last time. One of two things will happen. You will either say, someone gives you the data, you do your stuff, you will either go back to them and say, I did it. In other words, I learned, and here, here's a final hypothesis G, go. You can deploy it safely, or you will tell the guy, I failed. And it's important to realize that it must be possible to fail in a machine learning problem. Okay? It's not possible to guarantee success. Okay? And, you know, you will say one of these things, and in either case, with high probability, whatever you say will be correct with high probability. Now, we don't know ahead of time which of these you are more likely to say. It depends on how good of a machine learning person you are, how skillful you are at choosing the hypothesis set and the features and whatnot. Okay? And, you know, and also, you know, what kinds of target functions are you attacking? If all you ever attack are the world's most complex target functions, you will often say you failed. Okay? And if you fail, you fail. The point is, you will say one of these things, and with high probability, you will be correct. Okay? And, you know, in some sense, you know, that places you into these blue categories in this same. Okay, so what the theory says, okay, so you will look and you will see that E in is close to 0. So you think that you have learned, okay? You think that you have learned, so okay, you think that you have learned, and it is indeed the case that E out is approximately equal to E in. So not only do you think that you have learned, you know, you consider yourself to have learned, but it is indeed the case that you have learned because your E in matches to your E out. Okay, so this is what the theory says, and in that situation you'll say I did it. Okay, in the other situation that might occur, E in is, let's say, much greater than 0, but you still maintain E out is approximately equal to E in. Okay, and so in this situation, you know, your E out is large, so you haven't learned, you know not, you haven't learned, but you know that you know not. So what the theory of learning sort of establishes is that with high probability, you'll be in one of these two blue worlds, which are good. Okay? I mean, ideally you'd like to be in the top blue world, but at least in the bottom blue world, you know, you're not conning yourself into thinking that you have learned. Okay? And you go and perform a disaster in deployment, which is what this red world is. Okay? So the crucial thing that the theory of learning establishes is that it allows us to avoid this disastrous red world, where, you know, in this red world, E in is approximately equal to 0, but E out is much, much bigger than 0. You know not, but you think you know. It's a disaster. Okay. Now, you know, it's possible that with some probability, you know, you can also get into this world with low probability. So what the theory of learning establishes is that with high probability, you will be in one of these worlds. So with high probability, you will either, you know, say that you failed, and indeed you did fail, so your E out is large, or you will say that you succeeded, and indeed you did succeed, so your E out will be small. Okay, we don't know which of these worlds will happen, but whatever world happens, you will be correct in whatever conclusion you make. Okay. And then, if this world happens, oh, bingo, you can go and deploy your system. Okay, so, let's now let's get a little bit more into the weeds and talk about this formula that we established last time. Okay, so let me erase. Give myself some space.